Right, going through the need to know. So we know that momentum is conserved in a system. That means the total momentum is the same as the total momentum after. The individual momentum of the two objects can change. It's just the total amount that has to stay the same. Isolated means there are no external forces, so nothing outside of the system exerting a force, so like friction. If I have two carts hitting each other, obviously there's a force between the carts. That's an internal force, so that does not count. Elastic, kinetic energy conserved. Inelastic, not. When they stick together, that is always going to be inelastic, meaning I will always lose kinetic energy when they stick together. And always, momentum will be conserved. Doesn't matter if it's elastic or inelastic, momentum is conserved. That special case for elastic, when they're equal masses, the two objects switch velocities, but very, very rare. In a collision, the two objects have the same change in momentum, right? When one loses, the other one gains. They'll have the same impulse because these two mean the same thing. They'll have the same force because F of A on B is the same as B on A. And they'll feel the force for the same amount of time. If they have different masses, they'll have different acceleration and different change of velocities because F equals ma. If this is the same, A will only be the same if m is. And delta P equals m delta V. They'll have the same delta P, but they'll have different delta V's if the m is different. Impulse, same thing as change in momentum. If you have a constant force, then you can just do F delta T to get the impulse or change in momentum. If it's a changing force, then you have to actually do the area under the force time graph. In a collision, the center of mass will remain at a constant velocity. So whatever the center of mass velocity was before, it'll stay the same, or if it was rest, it'll stay velocity of 0 unless there's an external force, something outside of the two object system, exerting a force on the two objects. We need to be super careful with directions because directions matter for momentum. For energy, it doesn't, because if I have 1/2 m negative v squared, that negative sign is going to become a positive, so I don't really care about the sign for energy because energy doesn't have direction, but momentum it does. Our two equations, P equals mv and delta P is F delta T. We also need to know that delta P can be found by m delta V. That is super important. It comes up a lot. All right, 2 kilogram moving to the right with a velocity of 5 sticks to a 0.25 kilogram that's moving leftward. So I'm going to put a negative speed of 10. And then, it says it sticks to. So we've got 2 and the 0.25 going question mark. Because I want to find the kinetic energy after. So first I need to find the missing velocity. So 2 times 5 plus 0.25 times negative 10 equals 2v plus 0.25v. Momentum before equals momentum after. Momentum before was 7.5, 2.25v. So then my final velocity is 3.33. So this is 3.33 meters per second. Now I want to find the kinetic energy. You basically have 2.25, right? These two masses make a total mass of 2.25, all of which is going at 3.33 squared. And then you just put this in your calculator, and that gives you your final kinetic energy. It's 12.5. Here we're looking at a force of a ping pong ball as a function of time. We've got the mass. I see that it's initially moving to the left. So I have an initial velocity of negative 8. And I want to find the velocity after, so I want to find v final. First, I have force time graph, so I'm going to find the area. The area here is base of 3 times height of 6 divided by 2, which gives you 9, except for this is in milliseconds, so you need a times 10 to the negative 3. You don't have to memorize that. That's on your equation sheet. You see milli, it says 10 times negative 3. So instead of 9, this is actually 0.009. And the area represents your change in momentum, so delta P equals that. Delta P is also m delta V, so I can plug in mass and my change in momentum, and I get a change of velocity of 9. Now 9 is not what I asked for, that's how much the velocity changed. If my initial velocity is 8 and it changes by 9, my final one will be 1. I think of it as that this change is positive, so I'm gaining 9. If I have negative 8 and I gain 9, you're just adding 9, it becomes 1. You also can do v final minus v initial. That is 9 equals v final minus negative 8. It becomes a like this, you have to subtract over. I think it's easier to do the change just thinking like, oh, okay. Alright, these two collide and stick together. How much mechanical energy is transformed into internal? Mechanical energy is talking about both kinetic and potential. Here, we're just talking about kinetic. It's not like the potential is changing. So how much of the kinetic energy is going into some other form of energy? That means basically how much kinetic energy is lost. So let's find, first of all, let's find the velocity after they stick together. So that's 3mv plus m negative v equals 3mx plus mx. That's 4mx here. Plus m times negative v is just 3mv minus mv, right? Put the negative out front. 3mv minus mv is 2mv. M's cross off, divide the 4 over, that becomes 1/2 v. Alright, I want to know the kinetic energy that was lost or goes into some other form of energy. So I'm going to find the kinetic energy before. V4. So kinetic energy before is 1/2 3mv squared plus 1/2 m negative v squared. There are some of you who just put the minus out front instead of the negative v. For momentum, that's fine. For this one, it is not fine because negative squared actually is going to become a positive. So this is still a positive. So this is 3/2 mv squared plus 1/2 mv squared, which is just 4/2 or 2 mv squared. So that's my kinetic energy at the beginning. Now my kinetic energy at the end is just 1/2. You can think of this as just 4m and a velocity of 1/2 v squared. So 1/2 squared is 1/4, like this. The 4 and the 1/4 cancel out, so it's just 1/2 mv squared. So this is how much I started with. This is how much I ended with. How much was lost is just the difference between them. So if you do this minus this one, then you get a change of 3/2. So that's how much energy was converted into some other energy that is not mechanical, not kinetic or potential. So heat, sound, deformation, etc. Right here, you will notice that this is a graph of the position as a center of mass, the position as a function of time for center of mass. We notice that the momentum is not staying constant, right? I have some velocity and then it got faster, so I had some external force that must have been applied to change the momentum of the system. I want to know what the change of momentum is. Normally when we're doing change of momentum, you do F delta T. You'll notice that you don't have anything about the force, so I'm going to use my other way of finding it, which is m delta v. I have my mass, it's 2 kilograms. I'm looking for the change in velocity, so let's look. Right here, I'm going up 2 meters in 2 seconds. This part has a velocity of 1. Here, we're going 3 meters in 1 second, so that's a velocity of 3. Going from a velocity of 1 to a velocity of 3 is a change in velocity. Change in velocity of 2. So my change in momentum is just 4. Next one, again, position, time. So I'm not doing area because I'm not trying to multiply force times time. Still looking for change in momentum, m delta v. I have my mass is 0.5, so I just need to find my change in velocity. So at first, it looks like I'm going 2 meters in 2 seconds. This is a velocity of 1. Now I have 3 in, this one is actually negative 3, because that's a negative slope. I have a negative velocity right there. When you find your change in velocity, negative 3 and 1 is not a change of 2. If you do v final minus v initial, negative 3 minus 1 is actually a change in velocity of negative 4. Oops, that doesn't look like 4. So when you do mass change in velocity, you actually get negative 2. Alright, kid riding in a wagon has a ball. And the wagon's going at v. Then the kid throws the ball out of the wagon. It is now going at 2v. The wagon is going to be slower than v because it just gave this guy some of his momentum to the ball, so they're going a little bit slower. I want to know what the velocity of the center of mass is. So the velocity of the center of mass is going to be constant, right? It's going to be the same as before because there was no external force. It says ignore friction. Here, there's some force between the guy and the ball, but I'm including both of them in my system, so it's an internal force because it's between both of them. So again, the center of mass velocity is not changing, it will stay the same. I don't really know how you're gonna figure it out from this, but if it's not changing, it stays the same as before. All of them were moving at the velocity of v, so the velocity of the center of mass before was v, so it's still v. Here we're looking which shows the momentum of the 3M. So I'm going to start with the negative velocity for sure, going this way. When these two stick together, because this one has the same velocity but more mass, it has more momentum, so when they're together they'll move to the left because the total momentum is to the left. So I'm still going to have negative, so negative and then I end negative, but because this is picking up this other mass and giving some of its momentum, this is going to be slower than v. So first cross off anything that isn't negative and that starts negative and ends negative, so A and B are wrong. C and D both start negative. D is actually getting faster, whereas C is actually getting slower, so C is your answer. Because I start with some negative velocity, and now I'm still negative, but it's not as fast as before. 3 balls, all equal mass, are attached to the spring and free to move. Ball B is at rest. These two are moving with the same speed, so I'm going to put V and negative V, M, M, M. So my total momentum, right now, I have MV, I've got negative MV and 0. So you should notice that your total momentum at the beginning is 0. Everything, not everything, these two cancel out and the other one's 0, so the total is 0. Now it says that ball A sticks to ball B, so these two are now combined because they're stuck together, and C bounces off, meaning C goes the other way. I want to know what direction A and B are going to move after the collision. Well, we know that the total momentum is the same, so it still has to be 0. If C is going this way and A and B are going the same way because they're stuck together, the only direction they possibly could go is it has to go left. Because if they both were going right, then you'd have a total momentum to the right. If this one just was at rest, then you'd still have momentum to the right. And we know our total momentum is 0 because there was no external force, so it has to go to the left. Now, it's not going at the same speed, right? I have 2 masses, they'll go slower than this one. Their momentums are going to have to cancel out, their velocities do not. But it is to the left to keep a total momentum of 0. All right, we've got a car on a freeway going, there's a mosquito. It's initially at rest and then they hit and stick together, I think. What happens to the total momentum? It remains the same because there's no external force. There's definitely going to be a force between the mosquito and the windshield, but it's not an external force because it's between the 2 objects in the system. Does the momentum of the mosquito increase, decrease, stay the same? I had a lot of people in class say these two have to stay the same because momentum is conserved. Total momentum has to stay the same. You can absolutely transfer momentum from one object to another. In fact, this one was at rest and now they are both moving, so the mosquito gained momentum because it didn't have any and now it does. If the mosquito gained momentum, how did I circle decrease? If the mosquito gained momentum, that means that the car must have given up momentum. So here I said because it got faster. Here you can think about it as, okay, well, if this guy, mosquito, got momentum, it had to come from somewhere, so it means that the car must have lost some. You also think about it, when you hit something, the car is going to slow down. Obviously, mosquito is like a super extreme example, so it's probably negligible, but we're saying it counts, so it decreases a tiny amount. Which changed its speed by more, the car or the mosquito? So obviously we know when they hit that the car's velocity is barely going to change. It's going to be so small it's essentially negligible, whereas the mosquito was at rest and now it's flying down the highway, so the mosquito changes by a greater velocity, and that is because it has a smaller mass. In fact, much smaller mass, so it has a much greater change in velocity than the car does. Now, which changed its momentum more? So what people do is they're like, oh, the mosquito has a greater change in velocity. That's a greater change in momentum. Or they say the car has more mass. That's a greater change in momentum because change in momentum is m delta v. Well, the answer is both, right? More mass means more, but only if this is the same. Greater change in velocity means more change in momentum, but only if the mass is the same. That's not the case, so I'm not going to think about it like that. I'm going to think about it as my total momentum is conserved. If the total amount of momentum has to stay the same, then if this guy gained, I don't know, 3 units of momentum, then that had to come from the car losing. So they had to have the same change in momentum. And I'm going to put 1 gains and 1 loses. And it's by the same amount, right? That momentum can't disappear, so if it's lost from one, then it went to the other. And it can't just appear, so if one gains a certain amount, it's because the other one gave it up. Which experienced a greater impulse? So impulse is F delta T, or you can think about it as change in momentum. We just said they had the same change in momentum, so they should have the same impulse. You can also think about it as F delta T. They should experience the same force. They shouldn't experience it for the same amount of time. The greater net force, so they have different masses, they'll have different accelerations, but they're going to feel the exact same force because the net force on the mosquito is from the car. The net force on the car is from the mosquito, so it's just the force between them, so it should be the same net force. Alright, we've got a 5 kilogram rolling down a hill. It has a height of 0.8 and it hits a stationary car of 3. So first things first, I've got my 5 that I want to come down, and I want to know the velocity that it's coming down with right here. So I have potential going to kinetic energy, mgh goes to 1/2 mv squared. I cross out the m's, because why not? 10 times 0.8 equals 1/2 v squared. That's 8. Yes, times 2 becomes 16 equals v squared, so your velocity is 4 at the bottom. So what that means is this 5 is coming down with a velocity of 4, and it's going to bump into this 3 kilogram that's just sitting there. When these two hit, it says they stick together, and I want to know what that velocity is. So I'm going to plug in now, 5 times 4, we're using conservation momentum because this is a collision, equals 5v plus 3v. That's 20, divided by 8, you get a velocity of 2.5. So on the way down, we were converting energies. We used conservation of energy, went from potential to kinetic. Then the collision part, you will always use conservation of momentum. Alright, 2 pucks are attached by a spring. They're initially held at rest on a frictionless surface. They're then released. So this is my before picture. My after picture is that they're going different ways because the spring is going to push them apart. That's not an external force because the spring is going to be pushing each of them the same force for the same length of time. So that spring is internal to these two, right? It's the force between these two blocks. What do we know about their momentums, their velocities, and their kinetic energies when they go? And I also know that this one has 3 times the mass of this one. Alright, momentums. So some of you might be saying, okay, this one has more mass, that means more momentum. Only if their velocities are the same and they're not going at the same speed. And then if you're saying, okay, this one's lighter, it'll go faster, that's more momentum. Yeah, more velocity, but it also has less mass. So let's think about it in terms of conservation of momentum. Your total momentum before, when they're both at rest, is 0. So that means that my total momentum after has to still be 0. So these two have to cancel out momentum. So they have to have the same magnitude, one positive, one negative. You also can think about it as they have the same change in momentum. So if this guy has a change in momentum, I don't know, positive 5. This one has a change in momentum of negative 5. And because they both started at 0, then it would end up as positive 5 and negative 5. That's the other way to think about it. Their velocities. They do not have the same velocity because they're going to have the same momentum, but this one has less mass. So the puck 2 is faster because they have the same momentum, but this one has less mass. So I'll have a greater change in velocity, it'll get faster. Kinetic energies. Kinetic energy is 1/2 mv squared. This one has 3 times the mass, but this one has 3 times the velocity. You'll notice that the v gets squared, so having a greater velocity actually matters more for kinetic energy than having a greater mass. So puck 2 has the greater energy because it has more velocity, and the velocity is squared for the kinetic energy. Alright, a force versus time graph. We want to know is the momentum increasing or decreasing. So that's got whatever. This is roughly a triangle. We're going to look at the area under the curve because we want to find change in momentum, which is F delta T. So that's multiplying force times time, so that's area. So height, base, over 2. So that's my change in momentum. And this is a positive area. So if my area is positive, my change in momentum is positive, which means that I'm increasing momentum or gaining momentum because the change is positive. All right, we've got a shell. It breaks up the larger piece. The larger piece is 3 times that. And this was initially this way, going to be 4m. I want to know the velocity of the center of mass. Some of you try and find this velocity. You can do that. It's totally useless because I don't care what this velocity is. I want the velocity of the center of mass. Now, it's hard to find it given the 2 masses and the 2 velocities, but I know the center of mass velocity stays the same, so I can just ignore this. Whatever it was at the beginning is at the end. All of it is together, moving the velocity v naught. The velocity of the center of mass is v naught, so it stays v naught because there is no external force. This explosion between them is an internal force because, again, it is like the force between these two that explodes them apart. We have a 30 kilogram object initially traveling with some velocity. We've got this force, and I want to find the net change in speed from 0 to 5. So force time graph, I want to find delta V end goal, but I can find delta P first by doing the area. So I'm going to make this a positive triangle right here. And then we're not always going under. I know I call it area under the curve, but it's really to the x-axis, so if it's under the graph, it's actually negative. So this one I did 200 times 3 over 2, which is 3. And then here I did like 2 times negative 100 over 2, which is negative 100. So if I have positive 300 and negative 200, then my change in momentum is positive 200, right? Add those together. And then delta P equals m delta V, 200 equals mass delta V. Divide the 30 over, I got my change of velocity is like 6.67. So obviously if we're choosing between 7 and 14 for 6.67, 7 is the better answer. And then my answer, I got the change of velocity, I got the net change in speed and velocity, find the change of. I did not get a negative answer. I got a positive answer, so my answer is 7. I'm gaining 7 meters per second in this time. Yes, I ended with a negative force, but I gained more momentum than I lost right here. So I overall still gained. 1.5, moving to the right with the velocity of 5, sticks to a 0.25 that's initially at rest. What's the resulting speed? So momentum before equals momentum after. 1.5v plus 0.25v, that's 1.75v. This is 7.5? Yeah, 7.5. And then you divide over, you get your velocity is 4.28 meters per second. And we knew it had to be less than 5. I'm picking up a much smaller mass than I'm coming in with, so it's not going to slow down that much. This is very reasonable. The kinetic energy, does it increase, decrease, or stay the same? So you can actually calculate what the kinetic energy before is and the kinetic energy after. I did not, because I know anytime they stick together that this is going to be an inelastic collision. So you're going to decrease or lose kinetic energy. It didn't disappear, right? We know that energy is always going to be conserved, so this means it goes into other forms of energy. So like sound, heat, sometimes when things crash they like break, so there's like energy in the actual object when it breaks, stuff like that. Alright, we want to know, is there a net external force on the system? So asking, is there an external force, is basically asking, is the total momentum conserved? Right? Because if it is conserved, then no, there's not an external force. If it is not conserved, then yes, there was an external force. So I have velocity graph. So if we look at cart 1 has a negative change in velocity. Cart 2 has a positive change in velocity. So I'm going to say cart 1 and cart 2. I have a negative change in velocity and I've got a positive change in velocity. Now these two have different change in velocities. Cart 1 has a greater change in velocity. This one has less change in velocity than the other one, because I'm going from like 25 to -5, so that's like a 30 versus it's like a 15 jump. So a greater change in velocity. Now a greater change in velocity does not mean that momentum is not conserved, because I regularly have one object changing more than the other. But in this case, it says that there are two identical carts. Identical carts means they have the same mass. Change in momentum is m delta v. If I have the same mass and different change in velocities, that means I have different change in momentums. So because I have greater change in velocity and I have the same mass, that means I actually have a greater change in momentum for cart 1, and I have less change in momentum for cart 2. And I'm just going to make a note, this one is negative and this one is positive. So momentum is not conserved here because I have the exact same mass and they didn't change velocities by the same amount, so they didn't change momentums by the same amount, so there must be an external force. So we're between A, B, and D. Now, if we look, my greater change is in the negative direction, so overall, the change of the total momentum is negative. So that means I have a negative force, so I'm going to cross off A. And I have a negative force, not because one cart's momentum decreased, because I regularly have one cart decreasing and one increasing, but because it decreased more than it increased, because overall it decreased. My answer is I have a negative force because the system's momentum decreased, because my total P decreased. I want to know what the velocity, I want to know yet. The velocity at the center of the center of mass at the beginning was V. What is the velocity at t equals 6? So I know that the center of mass velocity stays the same except when there is an external force, and we just said that there was an external force. I have a negative external force, so that means I'm going to lose velocity. So instead of staying at V, which it should have, because I have this negative external force, it should be less than V, so slower. Alright, blocks M and 2M move to each other at the speed of V. The two collide and stick together, which shows M before and after. So M is going to start positive when these two hit. Because this one has more momentum, it's going to go to the left. So I want to start positive and then end negative. So all of these are 3. I only crossed off one of them. Now I need to think, is it getting faster or slower? So it's easier to think about this guy's velocity. I'm coming in at V for this guy. When they hit, this one has to give some of its momentum to the other. So he's going slower than V, which means they'll both go slower than V. So slower than V. This one is staying the exact same speed, right? It's like it would go from, I don't know, what was it, 3 to -3? Not what I want. This one's going from 3 to like -1. This one's going from 1 to like -3. This one's getting faster. That doesn't make sense, so it must be C. I start positive and I end negative, but slower than I was before. Here, so I've got 5 coming in towards some stationary. I know they stick together. At first I come in, and if you look at this change, so this one slows down a lot. Because I slow down a lot, that means I must have picked up a really big mass. So I must have picked up more than 5 kilograms. If I have 5 coming in, and I barely slow down at all, that means I must have picked up a small mass, less than 5, because I barely slow down at all. If I exactly half, so if you notice this is 1/2 the velocity, if you exactly half, that comes from doubling your mass. That means you picked up the exact same mass as yourself, because now it's 10, going at half the velocity. So I picked up exactly 5 kilograms. Alright, we've got a force time graph, and we want to sketch the graph of the momentum. So if we look, I have a positive force the entire time, so my momentum, so P should be increasing the entire time. T. So whatever my graph is doing, it's at least going up. It's never going down because I never have a force in the opposite direction. Now if you look, I have a small force, I'm not gaining very much. I gain a little bit more, still gaining, just not a ton. And then now I have a bigger force, so I'm gaining more and more. So again, I'm increasing the entire time, It's just that I'm gaining more and more as time goes on. So it'd be like starting out flat and just getting steeper and steeper. So I'm increasing, but I'm not gaining very much. I'm increasing and getting a little bit more. Now I'm increasing and gaining a lot, so that's steeper. So it maybe looks something like that. Here, so again, P is increasing the entire time because I have a positive force the entire time. Now if you look, in this time, I'm not increasing a ton. In the next, I increase even more, still the same. And then now I'm not increasing as much. So even though my graph is going up the whole time, I'm going at different rates. So I'm going up just a little bit, going up a lot. And then in here, it's still going up, just not as much. So going up a little bit. So maybe something like this. So going up steeper, going up, but not as steep. Here, this one moves to the left with the velocity of 3. This one moves with the velocity of 6. So because they're going to experience the same change in momentum, this guy has a change in momentum of 18. So then this one will have a smaller mass. So it'll have a mass of 3. That way their momentums cancel out. You can also think about the faster one has a smaller change in velocity. The faster one has a greater change in velocity, so a smaller mass. Their momentums have to cancel out, so that's not true. But because it has a greater change in velocity, it should have less mass. D. What is the velocity of the center of mass after the spring has been released? Well, initially they're at rest. So yes, this one's going faster, but it has less mass, meaning the center of mass is closer to here, but it's going slower. But I don't really care about all that because I know what the center of mass was before. The center of mass before was just 0 because they're at rest. So the center of mass will still be 0 after. Velocity graph, which one has a greater mass? So if we look, this one has a change in velocity. Object 1's change in velocity goes from 6 to 4, so that's 2. The change in velocity for object 2 is positive 1. Because they have different change in velocities, and I'm assuming that momentum is conserved because it didn't say anything about an external force, that means they have different masses. The one that has a smaller change in velocity must be the heavier, the more mass. So this one would be object 2 because it has a less change in velocity. If you're looking at delta P equals m delta V, if this is staying the same for both and you want more mass means less change in velocity. What is true about the center of mass of the two objects? So right now, they're separate velocities, so it would be like, I don't know, something coming in at 6, bumps into this guy going at 3, and then now they're stuck together and they're both going at 4. So here, you have 2 different velocities, 2 different masses, but I know that when they stick together, their velocity will be 4, so that means in here, their center of mass velocity must have been 4. Which one has a greater mass? So the greater mass, we just said, is the one that has less change in velocity, so that's object 1. Because in collision, they should have the same change in momentum. Totally okay to have different change in velocities, it just means they have different masses. Battleship fires a shell at ship A. This is a distance D. So ideally, it would land right here. This is like your target, right? What happens is that instead they explode and half goes over here at a distance